Okay, this video is meant to help you understand how to use what's called the binomial theorem. And it's a sort of a way to take combinations and combine them with expanding in order to find us a nice shortcut for how to find things like x plus y to the fourth power. Okay? X plus y to the fourth power, if you took it in sort of just a straight algebraic method, means that we need to take x plus y and we need to FOIL it or distribute it with another x plus y and another x plus y and another x plus y. Or essentially, if we expanded that into x plus y squared times another x plus y squared, we need to FOIL out or distribute out these two individual terms together. And if we do so, remember we do have a shortcut. We can say, hey, x squared is x squared, y squared gives you the last term. And don't forget that those inside-outside, if I took that x times y and y times x, we'd have two xy's in the middle. So both of these individually are going to come out to x squared plus 2xy plus y squared. Now, if I take those, I also need to FOIL that together now. So I'm going to need to take x squared times each part of that second trinomial, 2xy times each part, right, distributing each piece, and y squared times each part, again, of that second trinomial. And here's what you'll end up with. Again, by hand, that would take a lot more time. But again, all the green parts came from that x squared times everything in black. 2xy times everything in black gave me the blue, and everything in red from the y squared. Now we need to look through and find all the like terms. Now I've got an x to the fourth. I know I have a 2x cubed y, but notice over here I now have another 2x cubed y. So I'm going to have 4 of those. I've got an x squared y squared, but I have another 4x squared y squareds in the blue right here, and another x squared y squared in the red. So again, I'm looking through for all my like variables with like exponents. And essentially, in the end, finally, if we add all like terms, we're going to end up with that statement on the screen right there. You get your x to the fourth, 4x to the cubed y, 6x squared y squared, and then you sort of work your way back down. Notice now we go back to another 4, and then in the end another 1, if we look about those coefficients. You'll also notice that your x's kind of count downwards, and your y's sort of count upwards. We didn't have a y in the first term, but we've got a y to the first, a y to the second, third, and fourth going through. So there is sort of a hidden pattern behind it. And to help us with that pattern, one thing that can help us out is what's called Pascal's triangle. If I took various powers of that x plus y, again, we just looked at x plus y to the fourth, but if we took x plus y to the 0 power, that's of course going to be 1. Anything to the 0 power equals 1. Then I can do x plus y to the first and second and third and kind of work our way up those powers. And if you take a good look at it, you'll notice that on each one of them, again, you always get that x to the first power in the first term. Or if it's second power, we're going second, x to the third, x to the fourth. Basically, whatever your first term is to that nth power, to whatever power you started with. In the end, the second term, the y, also does the same thing down the sort of the back side of this thing. We've got a y to the first, y to the second, y to the third, depending on, again, what our n was, so what our x plus y to what power was previously. In the middle, we're going to get all those that other mixture of terms. And one thing you want to realize is all of those coefficients that we're getting when we FOIL this out, remember here's our 1, 4, 6, 4, 1 that we just got in that previous example. If I take away all the variables, well, basically we have Pascal's triangle. So one part of the pattern comes from those coefficients being those numbers in Pascal's triangle. And a great idea, another fun fact about Pascal's triangle, is all the numbers in Pascal's triangle come from combinations. Anytime you've got a combination of a number and you're choosing 0 of it, again, that's one way to do it. You can choose none of those objects. So we get those ones down that left side. But if you choose all of them, again, if I've got 3 objects, the only way to choose all 3 is literally to choose all 3, to take all of them. So I've got, again, one option for choosing everything. And if I find those combinations in the middle, they, again, are going to form that Pascal's triangle. One thing you want to be careful of is, again, whatever your n value is, clicking back here, whatever that power was we started with, that's going to be n, and that's the nth row of Pascal's triangle. But you're always starting from 0. That first row up top, right, that 1 on the very top, is n equals 0 as far as that row goes. Okay, so this would be the n equals first row, the n equals second row, third row, fourth row, fifth row, and notice again we've got n, c, 1, 2, 3, 4, 5, on the bottom row there. It also works to say, well, if I'm looking for the first number in a row, again, that means that r is going to equal 0. NC0, or 5C0, I should say, when n is 5 and r is 0, again, is always going to give you 1. So this becomes the r equals first, second, third, fourth, and of course, again, 5C5, when n is 5 and r is 5, we get that 1 on the end. Now, that means Pascal's triangle is one way to get those coefficients, but we could also individually find terms using those combinations. So a great way to kind of think of those expanded binomials is just to say that each term, term by term, all added together for the binomial theorem, is a combination of NCR, again, which row you're on of Pascal's triangle, or what that power is for a plus b to the n. And then r is which term you're on in that row. And again, we always start from 0 and count our way up to n. Each of the other terms, as we kind of noted before, the x, or right now the a value, that first term, is going to have its variables sort of count upwards. N minus r is going to start you at n if r starts at 0. But b to the r, that second term, the y values, are going to sort of count the opposite way. They're going to start out at 0, but then on each consecutive term, as n minus r gets smaller, r is getting bigger. Again, the first one's going to count its way down, the second part's going to count its way up. So let's look at one of those examples. X plus y to the fourth again. First thing to note is that n equals 4. And if that's the case, then we can set up each of the terms. I'm going to do 4c0, 4c1, 2, 3, and 4. I got all my coefficients out in front, which I can find individually. I don't have to FOIL out and add like terms. That's just going to handle itself. Then I'm going to say x for the first term is 4 minus 0. And again, y starts out at 0. So y to the 0 power, again, is going to be 1. Right here. 4c0 is also 1, but x to the fourth essentially is going to give me my 1x to the fourth. Over here, 4c1 was our 4. Again, y to the first, so I end up with a y to the first right there. Right? And our x to the 4 minus 1, right, as x goes to the next step, it's going to count down. X to the fourth, third, and again, going to become second power, first power, and x to the 4 minus 4, being a constant 1 again, is going to disappear in the last term. Whereas y, on the other hand, is going from 0 power up to first, second, third, and fourth. So you notice y to the first, second, third, and fourth in my example there, my expanded standard form. And again, each of the coefficients, 1, 4, again, 4 choose 2 is 6, 4 choose 3 becomes 4 again, and 4 choose 4 comes out to 1. There's my numbers from Pascal's triangle, right, in this first term, second, third, fourth, and fifth. Well, what that lets us do, again, is kind of take a shortcut. Notice that was a much quicker method. Yeah, it takes a little bit of setup, but you don't have to toil your way through foiling and trying to keep track of like terms. You can kind of go immediately to the terms and just find the numbers. So let's try that out a couple of times. Let's expand 2x minus 5 to the third, and we'll also try it as for just a couple of individual terms over here at the right. So what I would encourage you to do now is pause the video now and feel free to attempt the problem, and then in a minute I will bring up sort of the setup and walk you through how to find those pieces. All right, to just give you a little bit of help along the way, kind of step by step, first thing that I'm going to do is realize that n to the third here, that 2x minus 5 to the third, means that I'm going to have 4 terms. I'm going to start off with n being 3 in front of each of those c values, but I need to realize that, again, I'm going to start out at a 0 term here. Then I'm going to do r is 1, r is 2, and r is, again, 3, which I have that nicely written 3 there, so I think I'll just copy it over here. R is 3 there. Again, I'm going to add each one of those terms together as well. So I think I'll take a little shortcut here. And I need a couple of plus signs. So again, I'm going to add these together. So I'm going to put a plus sign in between each one of my terms. And then finally, each of those sets of parentheses essentially are the terms now inside my binomial. So I need a 2x minus 5 And I'm going to need that in each one of those terms. So I'm going to put a 2x inside of each of the first sets of parentheses. And then I'm going to put a -5. Now note the negative. Again, if it's -5, technically that's plus a -5. So let's make sure we include the negative. Since it's not included out in front with my plus sign, I need to put that in each term. Now we just need to assign each one of the powers. So we can take a second here. And I think we'll just write them in. But again, we're going to start out saying, all right, 2x is to the 3 minus 0. Or basically, it's going to start out to the third power. Then we're going to count our way down. And actually, we can take advantage of these sort of pre-written numbers here. We're going to need another 2, but I'm going to, again, need it as an exponent up here. Then I'm going to need this 2x to the first power down here. And finally, 2x to the 0 power, we're going to need over here. Again, our first term counts its way downwards, whereas the second term is whatever r is. So again, I can take that 0. I'm just going to place it directly up here. Take that 1. Click on the correct piece here. Take that 1, place it up top. And again, same thing with each of the others. R is always the power of that second term. All right, then the next thing to do is just find all the numbers. So again, 3C0, 3C1, 3C2, 3C3, you can either pop them individually in your calculator, or again, we can think back to our Pascal's triangle and say, hey, if we're doing n to the third power, that's the 3C0, 1, 2, and 3 here in the fourth row, right? n0, 1, 2, third, n equals 3 row of Pascal's triangle, so 1, 3, 3, 1, which quickly just gets us our red numbers down here in the problem. Again, the powers up here, 2 to the third, second, first, and constant, along with x to the third, second, first, and constant. They're my blue stuff down here. So I got 8, 4, 2, and 1, along with x to the third, second, first, and constant. And then the second term, again, counts upwards. So -5 to the 0 is 1. -5 to the first will stay -5. So you'll notice down here it becomes a -60 down here when we multiply it all out. As well as -5 squared is +25, and -5 to the third is -125. Then we just have to multiply it all out. 8 times a couple of 1s, 3, 4, and -5, 2, 3, and 25, and 1, 1, and -125. Our final answer down there at the bottom. Now, the nice part about only doing individual terms is I don't really want to expand this thing out to the 15th power. So this first question on the upper right, I don't want to do all the terms. I really wouldn't be a great fun. It's 16 different terms. Instead, remember the binomial theorem gives us a great shortcut. We could find any one term individually. So take a second, think about how would I set up a term that's going to end up giving me x to the fourth power. What would all of its pieces be? Its coefficient, its two parts, to affect the entire term. Try setting that up, and like I said, pause the video, and in a couple of seconds I will bring up the answers for you. All right, here's your answers for you. So again, taking that individual formula, we get the combination times each of the first term and the second term to their powers. Now one tricky part is we needed to end up with an x to the fourth. Well, remember the first term in our binomial is always raised to the n minus r. So if n is 15, 15 minus what would give us x to the fourth? We need an answer with an x to the fourth in it. Well, 15 minus 11, so if r were 11, we would end up with that 4. So really we want 15c11, x to the fourth, and -2, don't forget that negative, to the 11th power. Then it's just a matter of calculating the combination, calculating -2 to the 11th, realizing again it's going to stay negative, and realize the question just asks for the coefficient. So if we take that 1365 times -2048, we'll get our answer. The same thing happens for the problem down here at the bottom. The extra trick is there's that 2 in there. But again, find all three parts, multiply your three numbers, and you should be in good shape. I hope that helps you with the binomial theorem. If you have any questions, ask your teacher, and happy counting.